Hi everybody, welcome to another video in linear algebra, section 5.7, applications to differential equations. Differential equation is equation that has derivative in it, and the solution to differential equation is a function. Right. Now we have system of differential equation. The system of differential equation is in this form when the derivative equal to the linear combination of the function, or this can be written in the matrix form of derivative of x equal to a times x of t. X of t is owner of the function, and x prime of t as the vector is derivative, the vector of all the derivatives. Right. The solution to x prime equal to ax is a vector values function that satisfies the equation for all t in the real numbers, of course. There exists fundamental set of solution, and if a is n by n, then there are n linearly independent function in the fundamental set, and each solution is unique linear combination of this n function. Alright, we'll get back to that in a minute. And then we even have the initial value problem. Most importantly, the solution is that if we just have one function, then derivative is just going to be for x prime equal to kx, the solution is c times e to the kt, where c is constant. Right. Now to verify that x of t equal to c e to the kt is the solution, it's very easy. We just need to substitute back into this equation. If this is the function, we check the derivative. So that gives us c1 k e to the kt, and now we substitute in the function, first the derivative c1 k e to the kt, and then we have on the right hand side we have kx of t, and x of t is c1 e to the kt, so we have c1 k e to the kt times k. X of t is c1 e to the kt. Now both sides are equal, so that check. So the solution, if we just have one equation, that should be simple. Now when we have the system like this, of course this is a simple system. We just write x1 prime t is equal to 3 times x1 of t, and x2 prime of t equal to 5 x2 of t, and the solution we use that so we can solve the equation easily. We say x1 of t is equal to c1 e to the 3t and x2t is c2 e to the 5t. So that's simple. And of course the problem is, what if the matrix is not a diagonal matrix? Then things will get a little more complicated, and this is what we do now. So once again we have the equation x prime equal to a times x. A is a constant, the matrix, and then in that case we have the linear function, so this is important. So if that is that, it will be the linear combination of the function, and the function will be in this form: x of t equal to v, which is an eigenvector, and then e lambda t. Of course lambda is eigenvalue and v is eigenvector, and we have a linear combination of all of that. So if we have 5 eigenvectors and 5 eigenvalues, then we have 5 of this, and the linear combination is a solution. Right, keep that in mind, and we're going to use that. And right, so first, of course, I'll find eigenvalues and then eigenvectors. Right, find eigenvalues. We solve a characteristic equation. I'll try to write small because we may need a lot of space here. -1. First of all, let's just rewrite this in the form. So that would be we have derivative, and then we have the matrix -1.5, 1, 0.5, minus 1. So in that form, right? So -1.5, 0.5, 1, minus 1, minus lambda and minus lambda. Right, equal to 0. Right, so multiply this, -1.5 minus lambda minus 1 minus lambda minus 0.5 equal to 0. Multiply this out, -1.5 times minus 1 is 1.5 plus 1.5 lambda plus a lambda plus lambda square. All of them should be positive. Minus 0.5 equal to 0. And so we write this lambda square plus 2.5 lambda plus 1 equal to 0. Right. So the solution would be right. This look like lambda plus 2 and lambda plus 0.5. Yeah. So we have lambda equal to 2 and lambda equal to -2 and -0.5. Right. Next we have the eigenvalues. Once again, we should write small because this problem takes a lot of space. And vectors, once again, we're going to solve the equation a minus lambda I times x equal to 0 vector. Right. So for lambda equal to -2, we have the matrix minus 2 is plus 2 times x equal to 0 vector, which turn into 0.5, 0.5, 1 and 1. Reduced with echelon form. we should have that. And then we have x1 here and x2. Right, of course this is something we already, it's plenty of time. Right, so the solution eigenvector will be x1 and x2. x1 is negative x2 and x2 is 3, so just x2. Factor out x2, negative 1 and 1. Right, so that is the eigenvector. We just choose x2 to be 1. So we have for this is the first eigenvalues. We have first eigenvector now. We choose eigenvalues to be negative 0.5. Right. Negative 1.5, 0.5, 1, and minus 1. Minus negative 0.5, so that's a plus 0.5. Times x equal to 0. So that's negative 1, 0.5, 1, negative 0.5. Of course, reduced for echelon form. Actually, this one is the opposite of the others. But since the reduced for echelon form, we have 1 on top, so we just flip the 2 rows and subtract. Bottom line is, this is, of course you can use a calculator, but it's simple enough. Just going to do it by hand. So we have x1 and x2, and x1 minus 0.5, x2 equals 0, and x2 is 3. So we have x equal to x1, x2, and negative 0.5 x2 is equal to x1, and then we have x2. Factor out x2. We have this, and for simplicity, I would choose x2 to be 2, so we don't have to deal with the decimal here. So x2, actually the eigenvector x2 is negative 1 and 2, right? Make sure we multiply everything by 2. So here we'll let x2 to be 2, right? 2 times that, 2 times that. Right, now we have the values, we have the eigenvectors, eigenvalues, everything. Now we have the solution. It's called the eigenfunction. Yeah, it will be in this form. Right. So eigenfunction, we have x equal to eigenvector times e lambda t. So first we have first vector is going to be v1, or in this case x1 if you will, it doesn't matter. Yeah, just switch to v because here we write x as the function, to get rather confusing. Right, let's use v here. So it's not confusing when we write V1 e to lambda 1t, which is V1 is -1 and 1 e to the lambda which is -2 t. That is x1, and now x2, v2 e lambda 2t, v2 is -1 and 2, e lambda 2 is -0.5 t. Right, and the solution is the linear combination of these two. C1 x1 plus, of course, all of them are function of t, C2 x2, which will be C1 times that. Now in this case, we do have what we call is the initial condition. That is when t equal to 0, this equal to 5/4. So we let t equal to 0. When t equal to 0, I call the initial condition. Right. When t equal to 0, this equal to 5/4. Also when t equal to 0, this is e to 0 power is 1, e to 0 power is 1. So we just have the right hand side C1 -1 and 1 plus C2 -1 and 2, because e to the 0.5 when t equal to 0, that is 1, that is 1. And for this equation we solve for t easily, and I put in the augmented matrix -1 and 1, -1 and 2 times C1 C2 equal to 5 and 4, reduced to echelon form. Right, I have to pause the video because I think I made a mistake earlier. Right, so actually there's here, when we have x1 -0.5, x2, when we move to the other side, that should have been a plus. Sorry, so that's 0.5, 0.5, and turn to 1, 1, 1, positive, right? Yep, so -2 and 3. So after that we have C1 is equal to -2 and C2 is equal to 3. And finally we can write the solution. It's this one, but we do know C1 and C2 now. So -2 negative 1 and 1 e to the negative 2t plus c2, which is 3, 1 and 2 e to negative 0.5t. Yeah. So bottom line is the solution we'll call the eigenfunction will based on the eigenvector times e to the lambda t. Of course, if we have the initial condition, so when t equal to some particular values, we make that the function equal to that values, and we're going to solve for the coefficient. So the answer is what we have there. Right. Sorry about that, I make a silly mistake here. Right. Now, what happens when A is the organizable? Then we can write the solution in this form. So bottom line is A is decomposed into PD, P inverse, and we write like that. Now, if we let P inverse X equal to Y, so if this is Y, then we have the equation of X prime equal to P dP PDY, I think. Yeah. We have the Y, so that's what we have. Y here. And then since we have Y equal to P inverse X, multiply P on both sides, so X equal to Py, right? And then show the equation and turn into PDY equal to Py prime, and the derivative, it just becomes Py prime, and so we have P and P on both sides, multiplied by inverse on both sides, that cancel out, and we solve for this first, and then at the end we just multiply by P. Right. So bottom line is we're going to organize the matrix and then still use the eigenvector, eigenvalues. This time we're not using the eigenfunction. We use the eigenvector as P, and we write the solutions P times Y of t. Right. Before we do that, let's rewrite this system as x1 of t derivative, x2 derivative equal to 7, negative 1, 3, and 3, x1t, x2t, which is derivative equal to the matrix times the function. Right. Same thing, find eigenvalues, eigenvectors, but this time we do not use the eigenfunction. Eigenvalues, and we solve characteristic equation. So we subtract the diagonal and determinant of this equal to 0, so multiply it out. So we have 21 minus 7 lambda minus 3 lambda minus 10 lambda plus lambda square plus 3 equals 0, and that gives us lambda square minus 10 lambda plus 24 equal to 0, and the factor would be minus 4 and minus 6. So we have lambda equal to 4 and lambda equal to 6. Those are the eigenvalues 1, 2. Now find the eigenvectors. And we solve this equation. First, for eigenvalues of 4, right, so the matrix minus the eigenvalues right. So you have 3 and minus 1 and 3 and minus 1. Of course, we can just use reduce to echelon form, but from here to just subtract each other and we have 3, negative 1 and 0. But I said let's be consistent here. You see, even I did a bunch of this problem already and I still make a silly mistake here. You know that fraction, but that's okay. So x1 equal x1 minus 1 over 3 x2 equal to 0 and x2 is 3. Right. So we write a solution. x1 is negative 1 over 3 x2. Factor out x2 and multiply by 3. And let x2 equal to 3. We have the eigenvalues, have eigenfunction, eigenvector of negative 1 and 3. Right. By the way, let this be v1. It doesn't matter. That's it. Because this one we do not use the eigenfunction. The solution is not using the eigenfunction. We use the diagonalized support version. I now have 6. Right, so 7 minus 1, 3 and 3. Now we minus 6. Keep it 1, 1, 1, negative 1, 3, negative 3, and reduce to echelon form. We should have that where we have x1 minus x2 equal to 0 and x2 is 3. So the solution x1 is x2 and x2 is 3. So of course we can just choose x2 to be 1. So we have eigenvector one and 1. Right. So we find with that we can diagonalize that with P and D. So let's write diagonalize A. So the matrix P is equal to the column of the eigenvectors, so -1 and 3 and 1 and 1, and matrix D corresponding to that. We use this first eigenvector, so we use eigenvalues of 4 and 6. Right. So what next? What next is we show y prime equal to dy. Y prime equal to dy. Right. Y prime, we don't know, that's what we solve for, right? Equal to dy. Now this is easy, like the first example we have. So we just say y1t, y2t derivative equal to 4006 y2t. Right. Of course, that's what we did on the first example. So that's going to give us that. So we have y1 prime of t equal to 4y of t, y2 prime of t equal to 6 y2 of t, and each equation is simple, so we just say so y1 of t equal to e to the 4t. There's a constant to it, so let's say c1, and y2 is c2 e to the 60. So we have y1 and y2. So the vector y equal to c1 e to the 4t, c2 e to the 60, and finally x is equal to py. So we have x equal x1 t x2 t times p times y, p times y. Of course here we can just multiply the matrix out, but I'm just going to leave the answer as that. I don't know why I make the same mistake again. Make sure you don't do that on the test. That should be a plus. On V1. 3 is fine because that just now when we use P, that should be 1. Right. Remember, be mindful with that. When we move to the other side, that should be positive. Right. But that's what we have in this section. So we have the system of differential equation. Either we use the eigenfunction and we write the linear combination of those, or if we use the organization of A, use P and D. Using P and D, we solve for y prime equal to dy, and then x will be equal to py, and that's what we have. Of course, we can multiply that out. Right. So that is one of the important applications of eigenvalues and eigenvector. And that's what I want to cover in this section. As always, thank you for watching, and see you in another video in linear algebra.